Hi, I'm Becca, and this is my Oscillations lab. So, a quick introduction. The purpose of this lab is to model the motion of a spring mass system using a computational model, and then we will determine if energy remains constant in the spring mass system. So, we will use Newton's second law, the momentum principle, the period of oscillation formula, and the net force, gravitational force, and spring force. And we will also use the energy principle, and you can see those off to the side. So, a preview of results, the energy principle is upheld, and there is zero change in energy in the system. So the system will be the spring ball in the earth and the surroundings will be nothing. The forces will be used to calculate the change in position and the change in velocity of the system using the velocity update and position update formulas. Initial conditions, the spring length at equilibrium with the ball is 0.7 meters. The origin is at the attachment point. The y-axis is aligned with the spring. The frame rate in tracker is 10.53 frames per second, and the video is observed from frame 5 to the end. So details of experiment, the ball is released from rest at the initial position, negative 0.114 and negative 0.618 in the x and y directions, and I got those numbers from tracker. And then the period of oscillation in the y direction is 1.5006 seconds, and I got that from dividing the number of periods of oscillations by the total time. And then these are graphs of the x and y positions over time in their oscillations. So we calculate the mass, and then we calculate the position from tracker. The zero vector will be the starting velocity of the ball because it starts at rest, and the gravitational constant of the spring is calculated by the period of oscillation formula, which is T equals 2 pi times the square root of m over k, and then you solve for k. To find the relaxed length of the spring, you set the gravitational force equal to the spring force. Kinetic energy is 1/2 mv squared, and the gravitational potential energy is mgh. The spring potential energy is 1/2 times the stiffness of the spring times the compression of the spring squared. And there is a link to my code there. So our initial energies are previously calculated values, and then we just need to calculate the spring and gravitational force. So Newton's second law and the momentum principle can be used with the velocity and position update formulas to do this, and then we will calculate L and L hat to update the position of the spring. And when updating energies, energy change is the final energy minus the initial energy. So for example, if you're trying to find the total energy, you would do the final energy minus the initial energy, and then you just loop through that system. So as you can see, the total change in energy remains constant at 0, and delta K is constantly oscillating and is highest when the spring energy is lowest, which makes sense. The spring constant is constantly oscillating because it's high when it's stretched or when it's compressed, and when the spring is at its resting length, it's 0. And delta U grav varies with the height of the object. So as you can see here, the y position versus time graph has more variation than the x position versus time graph, but they both have very similar periods of oscillation and look remotely similar. So some sources of error, inaccuracy of tracker, inaccurate data due to problems with video or the inability to capture real motion in the y direction. There's not a smooth line for either graphs, and real motion must contend with drag and air resistance. So what does it mean with the energy principle? So is the energy principle satisfied? The energy principle claims that the change in energy is equal to the work from surroundings on the system, and the graph displays that the change in energy remains constant at 0, and the system leaves nothing in the surroundings, so the work is 0. And the kinetic energy plus the gravitational potential energy plus the spring potential energy is equal to 0. So the energy principle is satisfied. So what does it mean, period of oscillation? So I calculated these numbers from the x and y position versus time graphs. I found that the time taken for the 4 oscillations in the x direction was 6.648 seconds. And then I found that t equals 1.662 seconds. And in the y direction, I found that the time taken for 5 oscillations was 7.503 seconds. So then t would equal 1.5006 seconds. And then this is the formula I used for k. And then the higher time for the period of oscillation, the lower the spring constant. Conclusions, the energy principle is satisfied. The change in energy is 0 because work from the surroundings is also 0, and the computational model can predict with fair accuracy the motion of the ball, spring, and the earth system. Thank you.